Okay, last but definitely not least, okay, here we have key features of graphs, which is a whole lot of vocabulary, a whole lot of nitty-gritty details that we have to pay attention to. So I put a different type on every single one of these. So pay attention carefully to what we have here. On the first example, domain and range. Domain, how far left to how far right. Now, because this has an arrow on the left, it's starting with negative infinity. And as it goes to the right, it's stopping here and with a solid circle. So it's going up to an x-coordinate of 9, and that does include 9, so we use a bracket. The range goes as low as negative infinity as well, but up to, and one of the few times we look at the y-axis, even higher, it goes to 3 at some point. So that's a little tricky, because if you looked at the end point, you'd say, oh, it's only going up to 2, but no, it actually makes it up to 3 somewhere here. And again, it actually reaches 3. X-intercept's pretty straightforward, negative 5, 1, and 8. We would list those. And the y-intercept is just 1. Okay, we have no asymptotes. Let's move over here. Relative maximum point. So relative means it's like the top of a mountain or the bottom of a valley. This is not relative because it doesn't turn around. So we are not, that can't even be in the running for relative. It has to be an actual turnaround point. So this is a relative max. At the point it's asking for is at negative 2, 3. And we don't have any other peaks. So that's the only relative max. Relative minimum, we have no valley. Okay, we've got a kind of a plateau here, but because this is a flat line, it really doesn't ever reach a valley peak. So we have no relative minimum point. Our absolute maximum point happens to also be the same one that was our relative max, also is our absolute max. That doesn't always happen. The absolute minimum point this gets to is there isn't one. Because it goes towards negative infinity, no one can like fine-tune and say, here's the lowest point it reaches. There is no definitive lowest point. It keeps going smaller and smaller. So that does not exist. Average rate of change is just your slope from negative 2, which is this point, to 0, which is this point. That average rate of change is down to over 2. Down to over 2, which reduces to negative 1. So they'll ask you for the average rate of change in a certain interval, and that interval is starting point to ending point. That is a negative 1 slope. Increasing is also interval notation. Now this one is increasing from the beginning of time, so from negative infinity, and it increases all the way up, and this is where you have to strictly look at your x-axis. Do not let your y-axis numbers get the best of you. So from negative infinity, it's increasing, increasing, increasing all the way to here at negative 2. And then it starts to decrease from negative 2 to positive 2. And then from 2 to 6, it's constant, so that's a new category, from 2 to 6. And then from 6 to 9, it's increasing again, so we'll add that up here, from 6 to 9. Now, increasing, decreasing, and constant intervals always will use parentheses, so there's no debate ever. Positive intervals means above the x-axis. So starting at negative 5 to positive 1, it's not above the x-axis at negative 5 though, so we use a parenthesis. And it's also not above the x-axis at 1, so we use a parenthesis. It's also going to be above the x-axis again over here from 8 to 9. That does not include 8 because right at 8 is on the x-axis. But it does include 9 because that's a solid dot, and right at 9 it is above the x-axis. Your negative intervals are going to be from negative infinity to negative 5. It's negative again from 1 to 8, not including 1 or 8. Okay, so there's a look at that example. Now in number 2, because we know this is a radical graph, this is the dead end, so we'll give that a solid circle and we'll put an arrow on the end of that. The domain is from 4 to infinity, and that does include 4. The range is 0 and down, so we're technically from negative infinity up until 0. Remember, your interval notation has to always go smallest to biggest. So from negative infinity up to 0. Remember, infinities always get parentheses, and that does include 0. Your x-intercept is just 4. We have no y-intercept. We have no asymptotes on radical graphs. This graph is always decreasing, so there is no increasing. It's decreasing from 4 to infinity. Remember, increasing, decreasing, and constant intervals always have parentheses. There is no relative max because there's no peak of any sort. There is no relative min because there's no valley of any sort. The absolute maximum point that it ever reaches this is the highest the graph ever gets, so that's a y-coordinate of 0. If they ask for the absolute max value, you would say 0, because that's the highest it ever gets. But they're asking for the absolute max point, so we can give them the point, 4, 0. It decreases forever, so there is no absolute minimum. The average rate of change from 5, which is this point, now we can see pretty clearly that's 5, negative 2. If you couldn't, you would plug in 5, and you would get negative 2 to 8. That's 8, negative 4. Again, if you couldn't see it, you could plug it into the 8 into the equation and get it. So your average rate of change is your slope formula. Negative 4 minus negative 2 over 8 minus 5. So that would be negative 4 plus 2 and 8 minus 5, and there's your answer, negative 2/3. This graph is positive, never, and negative from 4, not including 4 because it's 0, to infinity. Now number 3 is tricky because we're only given the equation, so we really have to use our calculator and know how to use all those tracing features. So x to the third minus 2x squared plus 3x minus 1. Okay, the key features when you're looking at a graph and the points that you want to pick out right away are y-intercepts, x-intercepts, and any peaks or valleys, which it doesn't actually look like we have any. So this is interesting because I want to get a little bit closer in there. So I'm going to zoom in to the origin and see if I can see a little more clearly what's happening. So it crosses and it crosses. Okay, we want to know what this is. So that's the y-intercept. That's when x equals 0. And so I would do my trace feature and value. When I know the x-coordinate, I can just plug it in, and I get negative 1. And then I also want to know this one, which is the x-intercept. I don't have a value where I can plug in a y of 0, but I do have the root feature, so looking in the 0 feature. So looking for the 0, get your cursor to the left of that point, great. Get it to the right bound of that point, great. And then enter will tell you 0.43. We'll just go with 0.4. All right, so our domain, negative infinity to the left, to the right, positive infinity. Range goes as low and as high as it wants to, so negative infinity to infinity. X-intercept, 0.4. Y-intercept, negative 1. Asymptotes don't exist. It's increasing always. It's decreasing never. It's constant never. There are no relative max, no relative mins, no absolute max because it goes up forever, no absolute min because it goes down forever. Average rate of change from negative 2 to 3. We don't have those points, we need to find them. So negative 2 and 3. So to find that, oh, we got to back up. Back up. I just noticed that detail. We only want this graph from negative 5 to 5. So this is ending at negative 5 comma something. And it's also ending at positive 5 comma something. We got to find out what that is. So we can do second trace value. Negative 5, oops, go to, oh, it's not going to give me negative 5 because it's out of my window. So let me go back to Zoom 6. Second trace value, negative 5, gives me negative 191. Yikes. And then positive 5. option 1 value, positive 5 will give me 89. All right, change of plans. The domain is from -5 to 5, and we are bracketed, so we're including those. That's why I kept them closed circles and not open. Range, -191 to 89. Nothing changes with any of that. Increasing does, though. Increasing from -5 to positive 5, parentheses on those. No relatives still, but I do have absolute max and mins. Absolute max, 589. Absolute min, -5, -191. Okay, we're back at it. Average rate of change, -2. If I want to find, again, the coordinate, save time, I could plug in -2, or I could just have my calculator do the work. -2, -23. And 3 pairs with 17. So my average rate of change is, again, slope formula. That's going to be 40 over 5, which is 8. So we have a slope of 8 between -2 and positive 3. Which seems about right. It's a pretty steep slope. So there's our positive 8. The interval is positive from 0.4 all the way up to 5, and it is actually positive at 5. And it's negative, or below the x-axis, from -5 up to 0.4. It is negative at -5. It is not technically negative at 0.4, because 0.4 is a 0. All right. It's a rational graph. So there's a 0. This looks good. So our asymptote is at x equals 3. So our domain is all real numbers, except x cannot equal 3. The range is all real numbers, except your y value will never equal 1, where that asymptote is. We have an x-intercept at 0. We have a y-intercept at 0. We have asymptotes at x equals 3, that's the vertical one, and y equals 1. It's increasing, never, because this is going down. This is also going down. It's decreasing from -infinity up until 3. Nothing's happening at 3, so we can't include that. And then it's decreasing, again, from 3 to infinity. So we pretty much include it, say it's decreasing everywhere but at 3, because we don't have brackets on that. There's no relative max, because we have no peak. There's no relative min. There's no absolute max, because it will go up forever. There's no absolute min, because it will go down forever. The average rate of change from 0, which is here, to 4. We're going to treat that, we don't have an equation, so we're just going to assume this is 4, 4, and 0, 0. So your average rate of change, you can do your slope formula, or you can count your rise of 4, run of 4, which is 1. This graph is positive from -infinity to 0. Then it's negative from 0 to 3, not including 3. Then it's positive again from beyond 3 to infinity, because it's above the x-axis forever. It's never going to come over this. All right, our log graph. Now, you can sketch it based on what you know. You can cheat and use your calculator. I'll do that. So we'll do 3, and then math. We got to go down all the way to log base 2 of x plus 3, and we only want this from -3 to 3. So my x, -3 to 3. Now, this one's bracketed. This one's a parenthesis, so that's going to be interesting. So -3 is a bracket, so I'll keep a solid line. Looks like it's crossing at -2. 2, 3, 4. I'm not exactly sure what that y-intercept is, but it's crossing. And then +3. I'm not sure what that point is, but it's an open circle because that's a parenthesis. So my graph is going to do something like that. Now, I do want to see what that y-intercept is, because value, when x is 0, the y-intercept is 4.8 will go. So 0, we'll say that's at 0, comma 4.8. I want to see where that is. So 3 what? Second trace, value 3, comma 7.8. We'll do everything to the nearest tenth. And negative 3, well, that I can do in my head. Negative 3 plus 3 is 0. Log base 2 of 0 you can't do. Interesting. Second trace value. If you plug in a negative 3, you're going to get nothing. So there actually is no point there. Even though they use a bracket, actually you can't use a bracket there. That must be a mistake on my part, because if you actually had negative 3 is not in your domain, because that'll make you take the log of 0, and you can only take the log of positive. So, this is interesting because we have open circles. We haven't really looked at that yet. So our domain is negative 3 to 3, because that's all they're allowing. The range, how low does this go? What if I second traced and plugged in negative 2.999999999? The lowest this is going is like negative 119 point. It's approaching maybe negative 119.6. And it's going up until 7.8-ish. X-intercept is negative 2. You can see that. I think that's exact. Let's just trace it just to be sure. Left bound of my x-intercept, right bound, negative 2. Yep. So my x-intercept, negative 2. Y-intercept, we said, is 4.8. Asymptotes would be at negative 3. It's increasing always, so from negative 3 to 3, it's always increasing, never decreasing, never constant. Relative max, we don't have a peak, we don't have a valley. Absolute max, you don't have, because it technically keeps going up and up and up and up and up, but we keep getting infinitely close to this, so we actually never reach 7.8. See, that was parenthesized. So you couldn't say 7.799999999, because then someone could just add another 9 at the end and it would be even higher. So this is one of those weird cases we know about where it is, but we can't give a definitive number. 1 to 5, we need points, 1 comma something and 5 comma something. So second trace value at 1, we're at 6. Now this is a funny thing of asking 5, because our graph doesn't even get to 5, but pretending it does, let's open up our window so that we can trace this function. Let's ignore that interval for a second, because that's a little bit of a typo. Value at 5, we would be 9. So our slope would be y2 minus y1 over x2 minus x1, which would be 3 over 4. The interval is positive from negative 2. We'll go back to this again. From negative 2 up until 3. Not including negative 2, not including 3, only because 3 is open. If 3 had been a closed circle, we would have bracketed that. But then it's negative from negative 3 to negative 2. Okay? This is an exponential function, so just knowing what we know about it, it's exponential decay. It had a y-intercept of 30, but then it got shifted up 3, so it probably has a y-intercept of 33. But because also it got shifted up 3, we have an asymptote at 3, which is why it kind of flatlines. So a couple other things. As x approaches infinity, this notation, the y-coordinate, or f of x we can say, is approaching 3. It's approaching that asymptote value. As x is approaching negative infinity, so we're moving left on the graph, the y is approaching way up to infinity. That's a good notation to review as well. So domain here, this is going to keep going forever. There is no vertical asymptote, so it will keep creeping left. So it's negative infinity to infinity. The range, though, is from 3, which it will never reach, to infinity. 3 and up. X-intercept does not exist. Y-intercept. Y-intercept is when x equals 0. So we can plug that in. This is 1. 30 times 1 is 30, plus 3 is 33. So y-intercept is 33. Asymptote is this horizontal, y equals 3. Increasing never, decreasing always. Relative max, no peak, no valley, no absolute highest point, no absolute minimum point, because it's getting lower and lower towards 3, but again, there's no absolute lowest thing you could get. From 0 to 1, so we've got 0 comma, we already know that, that's the y-intercept, to 1 comma, let's see what that is. We plug in 1, 30 times 0.1 to the first plus 3, we get 6. So the average rate of change, 33 minus 6 over 0 minus 1, that's 27 over negative 1, negative 27. That should make sense that it's a negative average rate of change because you're starting way up at 33 and 0, or the 1 is like here. So you have a very negative slope. Positive always, because it's always above the x-axis, negative never. Okay. This is just going to be a quadratic with a vertex at 3, 1, opening down. So you'll get from your calculator, you can get some x-intercepts, you can get some y-intercepts, and you will have a relative max here, will be the vertex. Your absolute max will also be the vertex. I don't think there's anything else that's overly interesting on this one. Once you find your key points, then you can go through and answer all your questions. This one is, again, here's an absolute minimum, here's a relative minimum, here's an absolute maximum and the absolute minimum. We're increasing, starting here up until negative 1, then we decrease from negative 1, really we decrease all the way to here, which is 1, 2, 3, 4, 5, 6, then we increase again from 6 to the end. We're negative, aka below the x-axis, from negative 1, 2, 3, 4, negative 5 to negative 3.8-ish, we'd say. And then we become positive from negative 3.8 to 1.8-ish. Then we're negative again from 1.8 to the end. And we're not including this point as being a negative, so we would use a parenthesis around 1, 2, 3, 4, 9. Here, we would use a bracket, because we are negative at 1, 2, 3, 4. Negative 5, we are negative, so we'd use a bracket there. No asymptotes. We got some x-intercepts. We got a y-intercept. Average rate of change, just grab the point from negative 4, grab the point from positive 2, and then find your slope. Okay, this last section, which is finding inverses. There's all these different types of functions we have to be able to find the inverse for. So switch the x and the y. I start with a linear because that's the most straightforward. Solve for y. So you'll add your 7, divide by 2. So y will equal x plus 7 over 2. And so we just write it as f inverse of x equals x plus 7 over 2. Inverse here. Switch your x and your y. Now solving for y here, it's a little bit different. Divide by 2, that's all good. So here's where it becomes a little bit different, because when you take the square root of both sides, you have to remember your plus or minus. So this inverse has a positive radical and a negative radical. Positive radical and a negative radical. So the inverse here is not a function. Okay, this is f inverse of x. Not a function because it fails the vertical line test. We should have known that the inverse was not going to be a function because the original one, the parabola that opens up, fails the horizontal. So this is a function. because it passes the vertical. But its inverse will not be a function because it fails the horizontal, which is why its inverse fails the vertical. So this is not called a one-to-one function, whereas this linear one is, because this line passes the vertical and passes the horizontal. Its inverse, which is technically 1/2 x plus 7/2, has a y-intercept of 7/2 and a slope of 1/2, and it will pass both the vertical and the horizontal. So this one is a one-to-one. Exponential, switching the x's and the y's, no problem. Solving for y, divide by 4, because this is an exponential. Log base 2 on both sides, because we got to get that out from being trapped. Log base 2, that'll cancel that, and then subtract 1. So you get log base 2 of x over 4 minus 1 equals y, or f inverse. And that is a function because exponential growth passes vertical, passes horizontal, so we're all good. So this log is an inverse function. And when you graph these two, remember, they're going to be symmetrical to each other through this diagonal line y equals x. Okay, here's a log where we switch the x and the y. When we write the inverse of a log, we're going to get an exponential. Now to solve this, we first have to get the log all by itself, so divide by -2. And then this is trapped in here. So to get it out, we need to translate to exponential. So the base of 2 raised to the other side equals y minus 3. And then get y all by itself. Add 3, add 3. So 2 to the negative x over 2 plus 3 equals y, or in this case, f inverse of x. So the inverse of a log is an exponential. The inverse of an exponential is a log. The inverse of a line is a line. The inverse of a quadratic is a radical. And the vice versa will be true. I think we'll see on the back, yeah, number 14. Inverse of a radical. So if I switch the x and the y here, solve for y, so I have to add that 4 over first. I can actually square both sides here because I don't want to create a fraction. So I'm going to square both sides. 2 squared is 4, and then the radical squared will just drop the radical. And then, still solving for y, now I can divide by 4. And I would write this as 1/4 x plus 4 squared. See, it's morphing into that HK format. And then subtract 3. So I'd get 1/4 x plus 4 squared minus a 3 equals y, and that's your inverse function. So the inverse of a radical is a quadratic. A rational inverse. We spent some time on this, it's been a while, but pay attention here. So x equals 1 over y minus 7. Solving for y when y is in a denominator is tricky. You've got to cross multiply to get it out. That cross multiplying is going to require distributing, and then we have to solve for y, so we're going to add the 7x over and divide by x. So you get y equals 1 plus 7x over x. So guess what? The inverse of a rational is a rational. Polynomial. So switch them. Add 1 to both sides. Divide by 3 on both sides. And to get rid of the 4th power, we either take the 4th root of both sides or we raise to the 1/4 power. I'll take the 4th root. Now anytime you take an even root, you've got to remember plus or minus. And so that's not going to be a function either. Last but not least, another rational, but a little bit trickier than the one that we dealt with the last time. Because now we're solving for y, but it's in both spots. That's what's tricky. We have to distribute there, xy plus 2x, and then equals 2y. Now you have to get all your y's together, so I'm going to subtract this xy term over. And here's the trick, and here was our slogan. If you can't combine the y terms, remember we're solving for y, if you can't combine them to get there to be only one y in the problem, you have to factor them by GCF. So I'm going to factor out a y, which now allows me to only have one y in the problem that I'm solving for, and now I can get that y all by itself by dividing by 2 minus x. Oops. So y equals 2x over 2 minus x. And again, the inverse of a rational is a rational, but that takes a little bit more work than this one because we had y's in two places. Last bit on inverses here. We have a table of values where we're going to graph the original function, 4, 7, and 6, 5. It's kind of a weird looking function. It's doing this. But now it wants the inverse, graph the inverse. So that's just flip-flopping the points. So rather than negative 2, 0, 0, negative 2. Rather than 0, 3, 3, 0. Rather than 2, 6, we'll do 6, 2. Rather than 4, 7, we'll do 7, 4. And rather than 6, 5, we'll do 5, 6. Now remember, the order that we just graphed these in, this does something like this. So you should see the symmetry between those two. But also note, the original here failed the horizontal line test. So the inverse is going to fail the vertical. So is that a one-to-one function? No, because the original fails the horizontal line test. So the original is a function, but it's not a one-to-one function. And then here, 0, 5 is going to be 5, 0. This is 2, 3 is going to be 3, 2. This here is 4, a little bit less than 2, so we're going to go a little bit less than 2 with a 4. This looks like 6, 1, so we'll do 1-ish 6. 8 and even smaller, so even smaller, and 8. So here we've got, looks like exponential decay. And then we flip-flop it, and it maybe is a log. And so yes, that is a one-to-one because the original passes the horizontal and the vertical. So that is it. That was kind of a lot. That was key features, but also inverses. I almost should split that up into 2 days, but I did have it all in the same document, so that is the review of inverses and key features.